Let's get straight on, have a look at some of the basic electricity definitions and calculations, and we'll have a look at some examples as well. At the end will be a couple of combinations of equations which may make calculating power easier for you, so stick around. Don't worry about what electric charge is, you'll be scratching your head for days. Just think of it as the electrical quantity in something. It's just a physical property of matter, just like mass. I guess the difference is though that charge can be positive or negative. Just accept that and move on. Charge has the symbol Q and is measured in coulombs. Current has the symbol I and is measured in amperes. Why Q and I? Well, blame the French. Current is the rate of flow of charge, or the amount of charge per second. Look at this circuit. We have a current of 3 amps flowing from the cell to the lamp. This means that 3 coulombs of charge are flowing every second. In equation form, it looks like this. Current equals charge over time, or I equals Q over T. Let's use this equation in a couple of examples. Here, 10 coulombs are flowing every 5 seconds. What is the current? Current equals charge over time. So current equals 10 over 5, which equals 2 amps. In this circuit, how much charge can a current of 3 amps supply in 5 seconds? Well, charge equals current times time, and so charge equals 3 times 5, which equals 15 coulombs. The equation can be written in 3 ways, and here's also the triangle if you find that useful. Voltage is the change in energy per unit charge, or the work done per unit charge, because remember, work done is just change in energy. Voltage can also sometimes be written as potential difference. Don't get confused or scared by that. Remember, charge has the symbol Q and is measured in coulombs. Look at this circuit. We have a cell supplying 3 volts. This means that for every coulomb of charge moving through the cell, the charge gains 3 joules of energy. The lamp also has a potential difference of 3 volts across it. That means it takes 3 joules of energy for every coulomb of charge that passes through it. In equation form, it looks like this. Voltage is energy over charge, or V is E over Q. Let's use this equation in a couple of examples. Here, a battery provides 12 joules of energy to 3 coulombs of charge. What is the voltage? Well, voltage equals energy over charge, which is 12 over 3, which is 4 volts. In this circuit, a lamp has a voltage of 6 volts dropped across it. How much energy is given to the lamp by 5 coulombs of charge? Well, energy equals voltage times charge, which is 6 times 5, which is 30 joules. The equation can be written in 3 ways, and here is also the triangle if you find that useful. Next comes resistance and Ohm's law. Ohm's law tells us that for an ohmic conductor, like a resistor, the current through it is proportional to the voltage across it, provided the temperature stays the same. Proportional means that if we plot a graph of current against potential difference, then we will get a straight line. As I mentioned, examples of an ohmic conductor are a resistor or even just a piece of wire. In equation form, Ohm's law tells us that resistance is equal to potential difference or voltage over current. Using the correct symbols, that looks like this. R equals V over I. Let's look at some examples. We have a 32 ohm resistor with a potential difference of 8 volts across it. What is the current flowing through it? Well, I equals V over R, so 8 volts divided by 32 ohms equals 0.25 amps. This is a 12 volt lamp with a current of 0.5 amps flowing through it. What is its resistance? Well, R equals V over I, so 12 volts over 0.5 amps gives us 24 ohms. Here we have a 1200 ohm resistor with 3 amps flowing through it. What voltage makes that happen? V equals I times R, so the voltage is 3 amps times 1200 ohms, which is 3600 volts. So here are the 3 forms of the equation and the triangle if you find it useful. Power is the rate that energy can be changed. It has the symbol P and it is measured in watts. When we increase the current, we increase the power. When we increase the potential difference, we increase the power. Power can be found from the equation power equals current times voltage. Therefore, P equals IV. My desk lamp runs off a voltage of 12 volts and a current of 0.6 amps. What's its power? Power is current times voltage, so it's 0.6 amps times 12 volts, and that gives us 7.2 watts. If you look on the bottom of most appliances, you'll see that they've got a sticker on that tells you their power. This one is 2,750 watts. That's my wife's kettle. In the UK, our main supply is around about 230 volts, which is more or less the same as the rest of Europe. In the US, it's about 110 volts. To work out the current, we would do the power divided by the voltage. So that would be 2,750 watts divided by 230 volts, and that would give us around about 12 amps. If you look inside the plug for that kettle, you'll see there's a 13 amp fuse, which is just right for that appliance. So here's the equation in its three forms, and here's also a triangle if you find that useful. I promised you two bonus equations at the end, but before I give those to you, if you're finding this useful, then please do like and subscribe or even comment. If we combine the resistance equation with the power equation, we find we can get P equals V squared over R. Or we can get P is I squared R. Using those two equations can save you a bit of time rather than faffing around with two different equations. Hope you found that useful. Good luck. Here's something else to watch.